Okay, let's go. Hi, everybody. This is the Gardener community meeting. Today we have the meeting on Thursday afternoon because we have a guest from Colombia. So on the agenda we have Plamen, who will give an update on control plane migration. And then we have Mauricio from Kinfolk, who will present Inspektor Gadget. So Plamen, you can start.
Yeah, let me share my screen. All right, so can everybody see it?
Yes.
Okay, so control plane migration, basically first a few words just to remind everybody why we need it and why we and basically what the general principles are. So basically one of the reasons is, let's say that the seed has to be changed, but this operation would require the recreation of an entire seed. Then all the shoots from this seed could be migrated to another cluster and then migrated back to the recreated seed cluster. Another option would be, so another requirement would be if a seed needs to be rebalanced to basically allow for less shoots to be deployed on it and to have more shoots deployed on other seed clusters. If new seeds become available in a region closer to where the workers of the shoot are, we could migrate the shoot control plane to those seeds so that we can improve the latency between the workers and the shoot's API server and other components. Garner Ring is also a requirement because it could use the control plane migration to host Garner to basically migrate the control plane of a Garner cluster between the basically three clusters which will comprise the Garner ring. And of course, one of the most important maybe scenarios which we'll actually start tackling now is if a seed goes down and can't be repaired fast enough. And basically, if the seeds, you can't guarantee that the seed is reachable from the garden cluster, and the garden cluster is also maybe not reachable from the seed cluster, then it could make sense that all control planes of the shoot clusters located there can be brought to another seed so that lifecycle operations for the shoot can continue. And also, if any workload actually depends on contacting the API server, would just give suffer to a minimum downtime between the migration. Okay, so what exactly is the control plane migration? And basically, the most top view of it is that the shoot control plane components are migrated, which basically means that we destroy everything from the control plane on one seed and we restore it completely on another. The data in the shoots for the shoots etcd is saved in a backup bucket in the infrastructure provider and then restored once the new components are created in the destination seed. Of course, this means that to actually support control plane migration, we need to use infrastructure as a service providers that have storage backend right now. And the so the shoot infrastructure nodes, DNS entries, and other basically infrastructure as a service resources remain untouched. This is so that the workload of the users remains working. And yeah, as I said, the workload should not experience downtime. The only exception to this would be if the workload depends on connection to the API server, where again, it should only be a minimum amount of downtime. It should be around, let's say, 3 to 5 minutes. Okay, so here's actually the state of, let's say, two seed cluster and Garden cluster landscape. Before migration, I've omitted the API servers just for brevity, but yes, you know, all communications here happen with the respective API servers for the three clusters. And I've omitted the shoot shoot cluster because there's actually nothing special that we do there. We only touch the control plane. So both the guardralets on the source seed and destination seed constantly watch for shoot state updates and use some filter functions to check if they should be the one that reconcile or operate on that shoot cluster. And this filter depends on a condition, which basically says that if the shoot spec seed name is equal to the seed's name where the guardralet is running, then the shoot cluster should be handled by that guardralet. Of course, if the status seed name is not nil, which means that already a successful reconciliation has occurred, then we also check that the shoot spec seed name is equal to the shoot status seed name and that they're both equal to the guardralet seed name. And so how do we, why we need this? Because the way that we trigger control plane migration is by actually modifying the shoot spec seed name value to be equal to the new destination seed. And since we still need the first operation that I'll talk about briefly is first migrating or getting rid of the control plane on the source seed. And the guardralet in the source seed still needs to know that it's the one that's responsible for the shoot cluster. So if the seed name and if the spec seed name and the status seed name are different, then the guardralet whose seed name is equal to the shoot status seed name is the one who's responsible for the reconciliation or for managing the shoot cluster. Okay, so what actually is the migration flow? Right now, the way that we've ordered the steps to basically get rid of the control plane in the source seed is, as I said, first you trigger migration by setting the shoot spec seed name to the destination seed name. Then the migration flow makes sure that the API server, etcd, resource manager, and basically other critical control plane components are running. This step is required if the shoot has been previously hibernated or for some reason the pods of the API server, etcd, and so on are not running. And we need them to run because of the cleanup operations that we do later on. So first of those is to annotate all extension resources with Garner Cloud Operation Migrate. This will basically force the respective controllers to do migrate operations, which I'll talk about a bit later. Depending on the actual controller operation, the migrate could do some special logic, which just makes some shallow deletion of the resources in the control plane, or it could not have any special logic at all and just call the normal delete functionality of the extension controller. So after all resources are successfully migrated, we delete them because their finalizers are removed and they are safe to be deleted. Then we have to handle the managed resources. Basically set the keep objects field on all managed resources to true. This forces the resource manager once you trigger the deletion of all managed resources, the resource manager will actually not delete any resources it has deployed in the shoot cluster. So we do this again to avoid changing anything in the shoot cluster during the control plane migration. Then we migrate the DNS entries. So right now this step still isn't completely implemented. There's an open PR for it, which uses DNS owners in order to make it so that the DNS entries in the DNS provider do not have to be recreated. In the demo that I will show a bit later on, or currently, the DNS entries get destroyed during the migration flow, and then they get recreated during the restoration. Okay, so after that, we take a snapshot of the etcd, which right now is done by executing by calling exec command in the etcd pod. But I think later on we will be able to do this with rest command. Sorry, just a sec. Somebody is making repairs next to my flat, so sorry for that. Okay, so we take a snapshot of the etcd and we save it in the backup bucket for the etcd in the infrastructure as a service provider. As I said, in the future, we might not have to execute actually in the backup restore sidecar to do that, but just call some REST endpoint and take a snapshot like that. And then finally, once everything is cleaned up, we can delete the shoots control plane namespace and the corresponding shoot cluster resource. Okay, so basically after migration finishes, the state looks something like this. The shoot currently has no control plane on either seed, and the garnet in the source seed updates the shoot's status and sets its seed name to nil. This basically forces, as I mentioned, the previous condition, this for choosing the seed which to reconcile the cluster. This will force it to now use the seed name which is in the spec cluster, which we set at the beginning to be the destination seed. And also we modify the last operation type. So yeah, we modified it to type migrate at the beginning of the migration procedure. And now we set its state to succeeded. We've added some special logic in the API server that will increase the shoots generation once this shoot status yeah. So yeah, we'll increase the generation of the shoot once the status has been updated. And this will basically queue the shoot for reconciliation. And it will be picked up by the garnet in the destination seed due to the conditions in the Flutter function. Okay, so now the restoration flow, it's a lot simpler than the migration flow because it's basically the same as the normal reconciliation flow. There are only basically 3 steps which are different. So in the normal reconciliation flow, as you know, data for secrets and etcd encryption and basically other resources is dynamically generated. During restoration, we fetch this data from the shoot state and use it to create the secret resources and objects in the shoot's control plane. Basically, the data, I'll show this in a second, but the data in the shoot state it's not exactly the same format as it would be in the secret or the etcd encryption configuration. The reason for that is so that we can use this data for any type of resource. So for instance, if for one thing we right now use a secret, but then would like to use some other type of Kubernetes resource, then the change should just be during the deployment of the corresponding resource and not on the format of data that we keep in the shoot state. Then the etcd backup restore sidecar, once the etcd pod starts up, automatically restores the etcd from its latest snapshot from the cloud provider. and the deployment of the extension resource is executed, but it's in 3 steps. So we can't just deploy uh, the extension resource with this restore operation annotation. We first have to deploy it with another annotation, which is called wait for state. This basically forces all the controllers to not do anything. So right now this operation, so this annotation is handled in common code, which is shared by all extensions. So you don't have to worry about implementing it yourself. So then while this annotation is active, the status state and status resources fields are updated. This status resources fields, by the way, is new. So I'll talk about it a bit later. I think it's in the next slide. And after that, we basically create any resources which are listed in this status resources field. So yeah, these are resources which So these are resources which would be required by the extension controllers since they carry some state. They could be either secret or config maps. And so yeah, mostly used for secrets. And then finally we annotate the extension with this operation annotation restore, which forces the extension controllers to finally reconcile the um, extension resource and basically trigger the restore functionality. So this is, yeah, if everything works right, after successful reconciliation, the control plane should be now on the destination seed. And just as on the source seed, the should state sync controller, for which Sven had a presentation a couple of weeks back, will continue watching for updates of the control plane extension resources. And if there are any updates to their status state field or their status resources field, to persist that data in the should state. Okay, so saving the control plane's state, for this we use the should state resource. I presented this previously, but it has we've changed it a bit, namely by adding this additional resources array and the resources field to the extensions resources array. So the idea here, as I mentioned, is that some extension controllers during the reconciliation of their corresponding extension resources could require some additional secret data to be kept as a state. And since we can't save this secret data directly in the extension's status state field, since then we would have to encrypt the extension resources, we decided to just save them as a reference part of the extension state. And then the should state synchronization controller can read those references, then read the corresponding secret and add the secret, or actually any resources, doesn't have to be just secret, and add the resource to the resources array in the should state. And the gardenlet during restoration does the opposite. Basically, again, reads the references in the resources field here, part of the extension, and deploys the corresponding resource from the resources array here. Okay, so now, as I mentioned, the controllers have to now support 2 operations, which are called migrate and restore. They are defined as functions part of the actuator interface, which all extension controllers have to implement. Now, some For some controllers, we use a generic actuator where we've basically implemented that migrate and restore functionality. And for instance, all other concrete controllers that use this generic actuator will come with migrate and restore predefined. As a general rule of thumb, the migrate should be used to do some shallow deletion of control plane resources without deleting actual infrastructure as a service or shoot resources. Or if nothing has to be preserved, then it can just be implemented as a normal delete operation that just calls the delete function of the actuator. The same thing for restore. If nothing has to be restored, you can just call reconcile. Otherwise, it has to restore the state of the extension controllers from the extension resources status states and status resources fields. And yeah, it takes, so yeah, this data has been provided to those fields, as I mentioned during the restoration phase. And the idea is that we do not try to create new, already existing maybe infrastructure as a service resources. And mainly for the worker controller, we don't want to create new machines. So mentioning the worker controller, we've implemented the migrate and restore for it's in the following way. It has a second actually controller working together with the one that watches the worker extension resource. This second controller's job is to watch for machines and machine sets. And once it detects that a machine is created, updated, or deleted, this second controller updates the status state field of the worker controller, as you can see here. In this status state machine deployments map, it basically adds the machine sets and it adds the machines. So for the machine sets, we add all the entire spec and the entire metadata. For the machines, we do the same, the entire spec and the entire metadata. And also this here, which is very important, we have the status node field. So this is used during restoration by the machine controller manager so that it checks that this machine already exists and doesn't recreate it. Okay, so yeah, during restore, basically what the worker controller does is it reads the machines from the state field and just deploys them directly as Kubernetes resources. And the machine controller manager automatically maps machines to machine sets and machine sets to machine deployments without us having to take care of anything additionally. So for the infrastructure controller, it's a lot more simpler than that. It just takes the, during the reconciliation, if there is error or actually a successful reconciliation, it updates its status state field with base64 encoded config map of the Terraform state, which has been created by the Terraform pod running in the control plane. So then the migrate just simply deletes the infrastructure resources without deleting any, the infrastructure extension resource without deleting any resources in the infrastructure as a service. And the restore functionality just takes this encoded Terraform state from the status state field, deploys it as a config map, and then even if Terraform pod is started, it knows what basically what infrastructure resources have been created and does not try to recreate them. And one more place where we've implemented migrate and restore is the shoot certificate service. We need it there if there is a custom issuer because then a secret is generated, which corresponds to that issuer. So here, the migrate and restore are a bit different, since they're just wrappers basically for the delete and reconcile functions. And how we handle the state restoration is that during the restore phase, the kernellet deploys the extension certificate service extension. It sets its state to this basically secret reference. Then it sets these resources to the corresponding secret reference and deploys the corresponding resource that exists in the shoot state from the resource list that I mentioned a bit earlier. Okay, so that's it, I think, for the status update. So what do we still have to do? So yeah, we have to still document how to implement, migrate, and restore, and provide a bit more context on how the whole procedure works, and just the entire flow, which operation gets executed before each other operation, and then maybe provide some examples with what we've already done, as I mentioned, for the worker infrastructure and shoot certificate service controllers. We also have to migrate DNS entry without destroying and recreating them. As I mentioned, there is already a PR for that, and we should be really close to having it implemented. The migrate and restore operations have to be implemented for the container runtime extension controller as well. We've currently started working on the integration tests, and actually once we finish those and we are sure that everything works fine, we will finally allow editing the shoot spec seed name so that control plane migration can be triggered. In the demo now, I've edited it in my local Garden cluster so that I can trigger it. And of course, pretty soon we are going to start working on the bad case scenario, which is to migrate the shoot's control plane from a broken seed to a working one. Okay, and now while I'm showing the demo, maybe if you have any questions, you can go ahead and ask. So I've already started the my local Garden cluster ready. I have 2 seeds and just 1 shoot cluster. So as I said, I'll edit the shoot cluster and trigger the reconciliation. Okay, and now if I list the shoots, and we have to wait. Yeah, I think my seed just currently has some error due to vertical pot autoscalers, but the should get resolved pretty soon. And yeah, you can see that the migration has now started. And once that finishes, the restoration procedure will start, and then I'll show the shoot cluster, basically, that it's on the new seed. Okay, so any questions while we wait? Okay, and as you see, the migration finished successfully, and now the restoration procedure begins, which basically, yeah. You can see that it's processing. If I get the status, you can see that the last operation is currently restored. And yeah, it's gonna take just a while to finish basically just the basic reconciliation.
How long does the migration take overall?
So usually right now, I think around 5 to 6 minutes is something that's, yeah, usually around 5 to 6 minutes.
Do you still want to show something? Because we are already over the 30 minutes.
No, that's it.
Okay, then maybe there are some questions. We can't hear you.
Can you hear me now?
Yes.
Okay. One question, does the time required depend upon the number of shoots in that seed, or is it is there any parallelization that then all of those migrate in parallel?
So it's basically, I mean, the control loops, they're part of the maximum control loops of the garnet. So if there are many shoots currently and some of those shoots are getting reconciled, it might happen that the procedure will have to wait for them to finish reconciliation and can start reconciliation after that. But otherwise, there should be no dependency on the amount of shoot clusters.
Thanks.
And yeah, so right now we just want to make sure that everything works properly with this migration flow. And in the future, we might think of actually parallelizing some steps. So as you saw right now, we first complete the migration and then the restoration steps, but there are some options to run a few steps part of the restoration phase in parallel with steps part of the migration phase.
Okay, thanks, Plamen. Then we can go to the second half of the meeting. Mauricio, you can take over.
Hi, yes, sure. So
Hi.
I'm just going to share my screen.
I can see it.
Okay, so just to confirm, can you, oh, sorry, this is the wrong document. Just a second. Can you see my screen?
Currently not. Now I can see it.
Okay, great. So yes, hi everybody. So I'm Mauricio, and today I'm going to show you this quick talk about debugging applications in Gardener cluster using this tool, Inspektor Gadget. So I'm Mauricio Vásquez. I work as a software engineer for Kinfolk. I work from Colombia. This is not Colombia. I'm in the country in South America, not in the States, in the United States. Anyway, this is a usual confusion people have right now about them. Okay, so let's start. So what is the problem we want to solve with Inspektor Gadget? We know that debugging distributed application is hard. This is hard because usually a distributed application is composed by many different components that interact together. So knowing what is the component that is having issues is usually hard. Talking specifically about BPF tools, there are many different tools that are being developed in Linux right now for tracing applications with BPF. So for the users and also for us, this is difficult to understand what is the right tool to use. So there are many different options, and this is not clear what is the best one to use. And more importantly, many of those tools are designed to trace applications in your local machine. So basically you start the tool and you get information about the processes in your local machine, you get information about the whole host and so on. But if you want to use those applications in Kubernetes, this is not easy because those applications or those debugging tools are not designed for Kubernetes. So Inspektor Gadget tries to close this gap. So the main goal of Inspektor Gadget is to enable different tracing tools that we call gadgets to be used in Kubernetes. Basically, we are taking different tracing tools that are around there, adapting them to make them usable in a Kubernetes cluster. This is an open source project. We have a channel in the Kubernetes Slack, just in case you have any questions and you want to interact there. And this is the repository of the project. So what do we need for Kubernetes, or what are the special requirements a tracing tool should have for Kubernetes? The first important thing is the granularity of tracing. We want to trace by pods. We don't want to trace the single process. So tracing the single process is not that useful because when you are running an application in Kubernetes, this is not easy to know what is the PID of that application. And even if you are able to know the PID, maybe you want to know the whole information about all the processes that are running on a single pod and not a single process. Another thing is that we don't want to trace the system processes. We are mainly interested in processes running on pods inside the cluster. Another feature that is needed in order to use these tools in Kubernetes is to be able to filter by using Kubernetes labels. So for instance, you run the tracing tool and you say, okay, I want to filter all the pods we are given label. And the last thing we consider that is important for these tools is to have an integration with kubectl. So we want to avoid users or developers have to SSH into the node to install some tools there and to run the tools into each node. And we also would like to avoid the case where the developer have to deploy a new pod, then executing into the pod, and then starting the tracing tool into the pod. So basically what we are trying to do is to make all this process easier for the users. So Inspektor Gadget is integrated with kubectl and is composed of different gadgets. So this is the list of the different gadgets we have right now. Some of the gadgets are based on VCC. So we are taking some of the gadgets on VCC. VCC is a project for creating tracing applications using BPF. So what we are trying to do right now is to update or to extend those tools into the VCC upstream to make them compatible with Inspektor gadgets. There are other gadgets that we are developing ourselves. For instance, Traceloop and Network Policy Advisor are gadgets that we are developing. Okay, so let's get into the detail. So Inspektor Gadget is composed of two different things. The first one is a executable that runs on your machine. This could be the client. In order to install that, we could just download release from the repository or use Crew. Crew is a kubectl plugin manager, and with a single command, you will be able to install the Inspektor gadget. The second thing that has to be done is to deploy the daemon set on your cluster. So this is the part that runs on each of the nodes. And in some systems and in some operating systems, this is needed to install the kernel headers. The PPF tools require the kernel headers to be installed to work. And some of the some Linux distributions like Garden Linux in this case doesn't include this kernel module or the kernel headers. And this is something that we are trying to improve. We are asking many different distributions to include this IK headers module by default in order to avoid the users to have to install these, the kernel headers by hand. I give you more details about the installation process on the demo. So before going in the demo, these slides are available publicly. So if you want to follow the demo, I have a document with a step-by-step with the list of all the commands to follow the demo, just in case you are interested. Okay, so let's go to the demo and let me show you how to install a Inspektor gadget. So the first thing we need to do is to install the local plugin that is executed on your laptop. So I'm going to download a release from the repository, and the installation is very easy. It's just to download the release, to uncompress the executable. I'm going to move the executable to the path, so kubectl is able to find it, and that's done. So, right, so the Inspektor gadget plugin for kubectl is installed. Those are the steps that I have to follow. Okay, right now I will have to deploy the kubectl daemon set in the cluster. This can be done with this command. You can see how the daemon set and the different configurations needed for Inspektor gadget are deployed. So let's check if the deployment is ready. Okay, so it's in running state. We can even check the logs to see what is going on. Okay, so these are the logs from the daemon, from the gadget daemon. This is working right now. So we are almost done with the installation. We are just missing the installation of the headers on the different hosts. So in order to install the kernel headers, I will do a trick. Inspektor gadget runs in each of the nodes, and it mounts the host file system. So I will able to say root into the host and install the kernel headers in that way. So I'm getting a shell to the pod, then annunciation root to the node, and then I'm going to install the kernel's header there. Before performing the installation, I have to check if the /user file system is read-only. In this case, this is read-only, so I have to remount that with write permissions before performing the installation. So, okay, I did the remounting. Right now, these have write permissions. And I'm going to download the kernel headers. To save some time, actually, I'm not going to download that, but I'm going just to show you the different files that are needed. So this is the list of files that I need to install. I'm going to install them with this command. Just as a comment, these are the files for this specific kernel version. If you are running a different kernel version, you will have to install the specific kernel headers for that version. Okay, I got some errors about dependencies, but in this case, it doesn't matter. It's going to work anyway. So let's go out. And this is all. Our Inspektor gadget is installed in the cluster, and we have installed the kernel headers in the different nodes. Okay, so let's go through the demo of some of the gadgets. The first gadget I want to show you is the Network Policy Advisor. The Network Policy Advisor is a gadget that analyzes the TCP connections in a cluster, and based on that, this is able to suggest you a set of network policies to be used in the cluster. the use case we imagine for this is that there is a new person in a project and this person has to implement the network policies, but this person doesn't have a deep knowledge about the project architecture. So this person could use this network policy advisor to get a suggestion of the different network policies to use. The idea is not to do everything automatically. We are not pretending to replace the person that is creating the network policies. We are just trying to help him to make this easier. Okay, in order to show you this gadget, I will deploy this microservices demo for GCP. We don't have to know all the details about that. What is only important for us is that there are many different components, many different services, and there are many iterations for them. So this is an ideal case for the network policy advisor because we are going to have a lot of different connections on the cluster. So let me show a quick demo about that. So I'm going to get the description of the services is here. Just going to show you clicking what is there. So we can see that there are many different deployments and many different services. This is just to show you that this is a complex service that could be useful for us. Okay, so before deploying the service, what I have to do, I have to start the network policy advisor in a monitoring mode. So monitoring mode means that the network policy is going to capture the traffic and the cluster is going to save that traffic, the list of TCP connections in this file, and then we are going to use this file to generate the policies. So this is ready. We are capturing the traffic on the cluster. What we have to do next is to deploy the service. Okay, so let's create a namespace, a different namespace, and let's deploy the service. Okay, so the service is being deployed. By service, I mean the whole example, the deployment, the services, and the configuration, everything that is in this manifest. Okay, so the service is deployed. I'm going to check the status of the different containers, okay, of the different pods. Many of them are running. I'm just waiting for all of them to be running. This one usually presents some crashes before this is ready. So just wait some more seconds. So what is happening right now is that this monitor has deployed some programs into the different nodes to capture the TCP connection on that nodes, and the information is being saved on this file, right? Okay, so I think all of them are in running state, so I will stop this here and I will stop the monitoring. Okay, so the monitoring is complete. Let me show you the list of the different connections that happened while the service was deployed. Of course, this is not very relevant for us. This is just an internal representation of the network policy advisor. Okay, and right now we can use the report command on the network policy advisor. We pass the file with the different TCP connections, and then we can create the network policies. Let me show you the generated network policies. So this is a list of network policies that will allow the traffic that were captured to pass. So it will allow those connections, those TCP connections to pass. As I mentioned before, the idea is not to deploy this right now, but the user or the developer could analyze this and modify them as needed. Okay, so let's go back to the presentation. Before going in detail about the other tools, I want to give you a really quick introduction to BPF. So BPF is a virtual machine inside the Linux kernel. It allows to, okay, so the workflow is that there is a BPF program, is written in C code. This is compiled into BPF bytecode, and that BPF program is loaded into the Linux kernel. When the program is loaded, this is attached to different events that are called hook points into the kernel. A hook point is something like, for example, when a packet arrives to a network interface, or when there is a system call, and so on. So the kernel provides different hook points to be monitored by eBPF program. So the workflow of the eBPF program is usually, there is a kernel event. For instance, there is a new system call, then the eBPF program is called. The eBPF program collects some data about that operation, saves the data on a BPF map, and then a user space application reads that data and makes that available in some way to the user. I know the time is short. This is a very, very quick introduction. I think this is enough for us. Okay, so how is the integration of Inspektor gadgets with Kubernetes? So when the user asks or tries to run a tracing tool, the kubectl gadget uses the Kubernetes API server to execute a tracing tool inside the gadget pod. And that tracing tool installs a BPF program inside the kernel of the worker node to collect the information that the user is interested in. And then all the information is sent back to the user. Okay, let me show you the next gadget. So the next gadget is trace loop. This is designed to trace different system calls. We are able to capture the parameters and the return value of the system calls. What is really interesting about this is that we are able to filter by C groups. So we are able to capture or to collect together all the system calls that are executed in a given pod. This is based on eBPF. It uses the hook traces points and it uses overwritable run buffer. More details just in a second. And just to clarify, this is not only for Kubernetes, but it can also be used with systemd services. And actually, this is an independent project for Inspektor Gadget, so we are developing that independent to be used in other cases. Okay, so what is the idea behind trace loop? We think trace loop could be a next generation of strace. We are not able to use strace on Kubernetes because this is slow. So the overhead of strace is quite high, and having a strace for all the pods in a production system is not possible. But more importantly, this is not possible, or better, you have to install a strace before there is a crash. So if you have an application that is crashing, you have to know when the application is going to crash in order to deploy a strace before. This is, of course, a problem when there are unpredictable crashes because you don't know when the application is going to crash. So the idea we had for trace loop is implement something like a flight recorder. So we capture all the system calls with eBPF instead of strace because this is faster. We save these system calls into a memory buffer, into a per pod memory buffer. And then we only read that buffer in case there was a crash. There is an analogy with the flight recorder of an airplane. So the investigators only look at the flight recorder when there is a crash or an incident. The same happens with trace loop. Okay, so let me show you a quick demo about trace loop. So I'm going to run a pod here. And the logic here, there is something bad in the logic here, and this pod is going to crash. So we are running the pod. Okay, so there was an error. If I do kubectl git pods, we can see it, the pod is in error state. Okay, let's delete the pod. We don't need that anymore, right? So the pod, we don't have any pods in the default namespace, but we can use trace loop to get information about that. Oh, sorry. Okay, as you can see, there is a pod that was called multiplication, and this pod terminated 30 seconds ago. So we can show the list of system calls that was performed by that pod. So let me take the ID of the trace. Let me copy this command, and this is going to give us the list of system calls that that was executed by that pod. What I want to make clear is that the pod doesn't exist anymore. The pod already ended, but we are still able to get the information about the system call. So for instance, we can see that this one, the system call that was failing, it returned -1. Okay. I know the time is ending. I'm going just to do a quick demonstration, 1-2 more minutes about other gadgets. So I'm just going to create a shell here. And that shell, I'm going to run some commands. So the next gadget I want to show you is the bind snoop gadget. So this gadget allows us to understand when an application inside a pod starts to listen on a port. So I'm going to open a port with Netcat, and we can see here that there is an application that is listening on port 5000, as done here. I'm going to show you just another gadget. So this one is the capabilities gadget. So it allows to understand what are the capabilities that a process or that a pod is required. I'm going to execute some commands that require some special capabilities. For instance, creating a BTH pair, making a node, ping, and so on. And we can see here how this command requires this capability, this command requires this other capability, and so on. What is this useful for? This is useful in the case you are trying to define the capabilities that are required for a pod, but you don't know the details for the pod. So you could run the pod in a test environment with all the capabilities enabled. Then you could run this capabilities gadget to get the list of capabilities that was really used by that specific pod. And just before finishing, I'm going to show you another interesting gadget. This is the TCP tracer. This allows us to trace TCP connections inside the cluster. Okay, so this is running. Let me try to get the Google page. Okay, and we can see here the PID of the process doing the operation, the version of the protocol source, destination address source, and destination ports. This tool is really useful when you want to monitor the traffic on a cluster, but you don't want to use local commands on the cluster. Okay, so I think this is all. I have prepared 2 more slides, but as the time is done, I think we can skip them. So if you have any question, please let me know. Thank you very much for your time.
This was a fantastic demo. Thank you, Mauricio. I think I will have to take a deeper look myself.
Yes, sure. Actually, that's the idea. I know that
Yes.
just looking at the demo is not enough, but we have the instructions for everybody that wants to go to the demo at home slowly.
Very nice. Thank you.
Thank you very much for the invitation.
Any additional questions? Seems not to be the case. Then thank you to the speakers, especially to Mauricio. And goodbye. See you next time.
Thank you very much. Bye-bye.
Bye.
Bye-bye.